One of the more important applications that we'll put to this idea of the dot product is the ability to find the angle between two vectors. Now, that angle is something that you could hypothetically sketch and measure with a protractor or something with questionable accuracy if you were doing something two-dimensional. Later we're going to see an example where we do this in 3 dimensions, and everything works out exactly the same, but it's measuring something that you couldn't actually put a protractor on and measure. So I've taken the liberty here of writing down the u and the v, and then the v minus u vectors here. As you'll notice, if you have a vector u and a vector v, and you put them with the same initial point, then the vector that connects them, you would want, when you take u and this v minus u and add them together, to get the u and minus u to cancel and for you to get v. And that's because you're going to have the same path being traversed by doing either one of those. So what I want us to see from the law of cosines is that if you were to write down magnitude v minus u squared, that would be kind of like the side c squared that we saw in the law of cosines. Then the other two sides of this triangle are magnitude u and magnitude v, both being squared, minus 2 magnitude u, magnitude v, and the cosine of the angle enclosed by that u and v. So if we go ahead and look at our definition for magnitudes here, we know that they'll have a square root in each one of them. So what squaring them will do is essentially get rid of the square root. And then we just need to have v1 minus u1 squared plus v2 minus u2 squared equals u1 squared plus u2 squared, v1 squared plus v2 squared, and I'm not going to break out this other part here because we don't need to. All right? If you go ahead and expand out everything on this left-hand side, you'll have v1 squared minus 2 u1 v1 plus u1 squared plus v2 squared minus 2 u2 v2 plus v2 squared, and we know that's equal to this stuff up here. But if you'll notice, both sides of that equation have a v2 squared on it, and both sides of the equation have a u2 squared on it, and both sides of the equation have a u1 squared and a v1 squared, meaning that we have minus 2 times u1 v1 v1 plus u2 v2 equals minus 2 magnitude u magnitude v cosine theta. You can cancel out the minus 2's and you get the result that's promised here. Now the way you'll usually use that is to say that your cosine of the angle theta is going to be u vector dot v vector over magnitude u magnitude v, and then in order to find out what theta is, you can just take an inverse cosine.